Here's an example of an application using an exponential function. It's called population growth. So here we have 50 fruit flies that were put in a jar with an apple, give them some food to eat on for a bit, at 8 a.m. this morning. At 12 p.m. that same day, the jar contained 78 fruit flies. What is the growth constant for this population based on a per day population growth? And when will there be 200 fruit flies in this jar? So the first thing I want to do is I want to discuss the formula we're going to use. It's a form of a PERT that we found using the compound interest formula. In this case, the only thing I've really changed is the r to a k, so it's a growth constant. I created a function out of it, so it's the amount after a period of time is equal to the population in the beginning times e raised to this growth constant times how long it's been in there. And since we're doing t, we're going to represent t as days. Alright, so one of the things we have to figure out is how long did it take to start off with 50 and eventually end up with 78 fruit flies. Well, 8 a.m. to 12 p.m. That would be 4 hours out of 24. So 4 divided by 24, that's 1/6 of a day. So the period of time would be 1/6 of a day. Alright, and then plug in what we know into our formula. We know the population after a period of time, that would be 78. It's going to equal the beginning population, which was 50, times e raised to the k, times the 6th of a day. And then all we have to do is solve for k. So the first step would be to divide both sides by that 50, just to get it out of the way. So 78 divided by 50, that's 1.56. And if it comes out to be an ugly decimal, you can always use that store feature on your calculator. This is going to equal e to the, well, k times 1/6 is just k divided by 6. Multiply the top of the fraction, multiply the bottom of the fractions. Alright, now there's two ways of solving this. We can use the rewrite as a logarithm, or we can log both sides, or we can ln both sides. I'm of the habit of ln'ing both sides, but in this case I'm going to do it the other way and just rewrite it as a natural logarithm. Since the base is e, I know this is going to be ln base e of 1.56, the other side, is equal to the exponent, which is k over 6. And then to solve for k, we're just going to multiply both sides by 6. So we're going to get k is equal to 6 times ln of 1.56, which is approximately 2.67. Alright, so now that we have what k is equal to, we can go through and find out, that's the growth constant, we can find out how long it's going to take to have 200 fruit flies in this jar. So we're going to start over again with the original formula. We'll know what k is equal to this time. The one thing that we won't know is the time, and we know pretty much everything else. So instead of 78 fruit flies, we're going to be looking for 200 fruit flies at the very end. The beginning population is still 50, that can't change, because of the growth constant is that 2.67. And it's going to be times t. So the only thing that we don't know here is the t variable. Alright, to solve for that, we're going to pretty much start off the same way. We're going to divide both sides by 50. 200 divided by 50 is 4. So we're going to get 4 equals e to the 2.67t. And in this one, I'm going to practice the other method, which is ln'ing both sides. So I'm going to ln both sides. And what we'll end up with is, on the left-hand side is ln of 4. On the right-hand side, the ln and e, since they're inverse functions, will pretty much cancel each other out, and you're left with 2.67t. And then finally, to solve for t, we're going to get t is equal to ln of 4 divided by that 2.67, which is approximately 0.52. And since we were measuring time as in days, this would be 0.52 of the day. So basically 12 hours. Well, let's be a little bit more precise. 12.5 hours. Multiply that 0.52 decimal that's in your calculator by 24, and we end up with 12.5 hours. This population will be 200 strong. So 12 hours away from 8 a.m., that would be 8 p.m. So about 8:30 p.m. at night, there would be 200 fruit flies in this jar based on this growth model.